So in the previous part of the lecture on the solution of Kelvin problem, we ended up seeing all these points. First was that on the free body diagram. Second is that the body forces are zero. And next, since we are dealing with a two-dimensional object, and remember we were complex displacement potentials can be used only for two-dimensional problems. Okay. And then we use the equilibrium equation, first thing, right? We related the applied force to the traction and we wrote it in complex form, right? F in general is a vector. That vector, that components of the vector were written in a complex form. That does not mean F, the X component is not in is a complex variable or the vector itself is a complex variable. We are not talking about bivectors. We are only talking about vectors and which have been conveniently written as a complex number. The vector is conveniently written as a complex number. And then we chose the following answers. You will see in a minute. See, what are these potentials? The potentials are something which you derive certain quantities from, whether it is a stress potential or displacement potential. Since we are looking at displacement potentials, we are going to differentiate these and then get our displacement potentials. Right? And why did we choose logarithm of z? Logarithm of z was chosen because we are dealing with an infinite sized object, and when you differentiate log z, you end up with a quantity 1 by z, and 1 by z is nothing but 1 by r times exponential I theta. And you can write it as in the numerator exponential minus I theta divided by r. And if you see as r tends to infinity, the quantities will converge to zero. Every quantity which has the derivatives of psi or w will converge to zero. That is the reason why we have chosen logarithm of z as the answers. Okay. And then we use the standard displacement formulation. Okay. These are things which we have already done. I've already shown you what log z, what log z expands to and all. And we finished up till displacement. We said displacement would be continuous as you may keep encircling the region of interest, but your displacement should remain the same. It's not like the displacement should keep on multiplying or adding, right? So from there you got one particular equation and the relation between A and the complex conjugate of B, right? And then what we said we will do is we have just used the displacement continuity condition. And the next one which we said we will use is on the traction, right? Del dot sigma plus force is 0. And that using Gauss divergence theorem, we have converted that to sigma dot n plus f is 0. And sigma dot n, we have written it as integral of TdS. That's what we have written in slide number 3. Okay. And integral TdS, which is the traction, which is the condition relating traction, is something in lecture 15 we have derived the generic form, right? It is from a length S1 to a length S2, right? And for us, we are taking a circular region because let me see if I can annotate here. Uh, yeah, we had taken a circular region, right? And you had a force F. Okay, all I'm seeing is I'm trying to seek a region where where the point of force of application is encircled by my choice of contour. Okay, should I only choose circular region? No, not necessarily. You can choose any region of your choice. Just that if I choose a circle, it gets easier for me to compute. That's all. Okay, the force balance should always remain. The force should always remain balanced, regardless of the domain geometry and the size of the geometry, both. Okay, and I'm substituting my answers of both A and B, right? And I'm getting one simpler expression. Okay, and I'm going to substitute this in the given equation. In the given equation, we have chosen that the force F is acting in the x direction. So my Fy would be 0. So I get one more equation in terms of A and B. So using two equations, One is here and the second is in the previous condition on displacement, where you had A plus complex conjugate of B, and here you have we have a condition on A minus complex conjugate of B. So two independent equations and two unknowns, solve for them, you will end up getting this, right? So once you know A and B, you can identify your psi. And once you know psi, you can identify your d. What is d? D is the displacement, right? Displacement, complex displacement, which is u plus iv, right? U plus iv. And how do we get this displacement? How do we write it in terms of psi? It is given here, right? You know psi and w or omega, and you can identify displacement. And once you know displacement, you know that you can identify remaining quantities like strain and displacement, strain and stress. Okay. So that is all there is to this problem. Just that a conventional Kelvin problem is done in three-dimensional sense. Uh, Okay. Uh, it is sort of an extension to the Bose-Einstein problem. A conventional three-dimensional Kelvin problem is. Now we have solved a two-dimensional version of the Kelvin problem where the force is in plane, right? And it is an infinite object. And we have used complex displacement potentials. And once you know displacement, you can compute the remaining things of strain tensor and then stress tensor. The key in solving an infinite or semi-infinite domain problems is in choosing the answers such that you end up having a logarithmic term. Why logarithmic term? Because these potentials are differentiated most of the time. We don't normally integrate potentials to get our quantities. Okay, when you differentiate a logarithmic term, you end up with a 1 by r kind of term. Okay, and you want such a term because as r tends to infinity, you want all quantities to converge to 0. Okay, so that is the reason for choosing a 1 by a logarithmic of the complex variable term. Okay, so this is it to this problem. In the next lecture, we will see the application of an extension of this complex displacement potentials, and that extension is in the form of Laurent series. Okay, so in the next lecture, we will see an extension to this complex displacement potential. Okay, I'll see you then. Thank you.